Okay, so today we're going to go ahead and talk about resistance. When I think of the word resistance, I think of a group of people or someone like fighting off something and like pushing back against something. I want you to visualize that when you think about the physics definition of resistance. And it is just simply how much material resists the flow of current. So again, it's something resisting something, and in this case, it is an object resisting current. So in general, like I think of like things that are resistors, it's like lamps, like any sort of like device in your house, like anything that has current flows through it is a resistor of some sort. Cool. So if we think of materials that are good conductors, so good conductors. So things that are good conductors are like metal is a great example of a good conductor. Is it easy or hard for electrons to flow through those? You know, it's pretty darn easy. So those have a low resistance. So things like wires are made of like metals, oftentimes copper. So it's very easy, and we want it to be easy for electrons to flow through. While things that are good insulators, and insulators, so a good example of an insulator is like rubber or glass. So those things insulate. It's not that easy for electrons to flow through them. They have a really high resistance. So when we think about resistance, so the units we'll use, and I'll go ahead and put that up here, we'll use the symbol R for resistance, and our units are going to be ohms or omega. And I'll put that, so the Greek letter omega. And the symbol oftentimes used when we're drawing like a resistor in a circuit, and again, it's like a light bulb, something like that, is we'll use kind of like a squiggly line, kind of like that. So this right here is, I'll go ahead and highlight, that is a resistor. Cool. So the equation for resistance is going to be R. It's going to depend on three different things. And I encourage you to go ahead and guess in your head if you think of resistor, what it might depend on, and then check back in. But it is going to be rho times L divided by A. And again, R is the resistance, which is measured in ohms, or we could say omega. Rho is the resistivity. And that is, and I'll call it, so that again, that's rho. And the units of that, and I have it in my table over here, are omega times m. And the resistivity is like a property of a material. So materials with lower resistivity, and let's look at our table over here. So things with a low resistivity, looks like all these conductors have a very low resistivity. It's 10 to the negative 8. While things that are insulators, those have a very high resistivity. And things with a lower resistivity, it's easier for electrons to flow through them, and they are better conductors. Cool. L is going to be the length of the resistor. And again, the resistor is just whatever the current is flowing through, so length of resistor. We will oftentimes measure that in meters. And A is going to be the cross-sectional area of whatever like the current is flowing through. So in this case, let's say, or any case, let's say we have a wire, which will be the typical example. So let's say we have a wire. The cross-sectional area is if we just cut a slice of that wire and look on the top and see what we see. So that would just be a circle. So in this case, it would be a circle. Well, if you have, let's say, a rectangular type of shape, the cross-sectional area would just be like a slice of it, which would be that. And it would be either, if it's a square, long thing, it would be a square, or it would be a rectangle. And we'll go through a couple examples to explain. We're using our new resistance equation. So I'm going to go ahead and draw a picture as we read along. So a copper wire, 0.5 centimeters in diameter. Draw my good old wire. And this is the diameter. So that is 0.5 centimeters and 70 centimeters long. So a little bit less than a meter. So this is what, 70 centimeters? connects to your car's battery to start the motor. What is the wire's resistance? And again, it is copper is our material. Cool. So let's go ahead and write down our given. So for this, we know, so we have R, we have rho, resistivity, we have L, and we have A. And again, our equation is going to be R equals rho L over A, the cross-sectional area. So we want to find the resistance, so I'll put a question mark right here. Rho is the resistivity. So I'm going to go ahead and look at that table that I had at the top to see what the resistivity is of copper. And let's go ahead and just look up there. So copper, it looks like, is 1.7 times 10 to the negative 8. So let's go ahead and go back down there. So 1.7 times 10 to the negative 8. The length of the wire, and again, we're usually going to want our units in meters. So 70 centimeters is what? I'll just go through my conversion right here. 70 over 100 centimeters in 1 meter. Boom, boom. So this is just 0.7 meters. Well, A is the cross-sectional area. So it's like if you take the area of one section of this. Okay, so this looks like right here for shape. That looks like a circle. So the area is just going to be pi r squared in this case. R is the radius. Okay, so the diameter is 0.5 centimeters. So the radius is going to be half of that. The radius is 0.25 centimeters. Wow, and if I convert that to meters, that's essentially divided by 100, so 0.0025 meters. Cool. So then the area is what? Pi times radius, which is 0.0025 squared. Cool. Wow, now it looks like I can just go ahead and plug it all in. This is so fun. So rho 1.7 times 10 to the negative 8. L is 0.7. And then area is pi times 0.0025 squared. And again, make sure when you're plugging this in your calculator, you're using parentheses for all this. So when I put this in my calculator, I got 6.06 times 10 to the negative 4. So let's think about this. Is this a big or small resistance? This looks like a pretty darn small resistance. Does this make sense? Yeah, it's a copper wire. We want wires to have really low resistance, so it's easy for electrons to flow through. We don't want electrons to lose a lot of energy as they're flowing through, like wires. Cool. Cool. One little side example I just want to give is, let's say we have the same problem, but let's say this was a funky wire and it was like rectangularly shaped. So let's say it was something like this. If I can draw this, cool. Something like that. And then this, when we're finding the area of a different shape, so in this case, let's say it's like this, and let's say the sides are, let's say 0.5, and let's say it's a square shape, 0.5. So the area in this case, it is not a circle, but that is going to be a square, so the area would just be 0.5 times 0.5. And we use that in our area. Not in this case, but let's say it was a different kind of shape.